Hello there, welcome to the new lecture. After the end of this tutorial, you would be able to understand primary pump head calculation and its selection. So let's start. So this is the project layout. We have already determined the capacities of chillers, ACUs and the flow in each and every section of the pipe. So this data is tabulated already. Alright, so we have already selected the primary pump circuit over here. We have segregated this circuit from the main circuit. So if you see, what are the steps that we have already followed? The first one, we have determined the flow rate in the main circuit. Alright, after that we have selected the circuit for which we are designing the pipe or selecting the pumps. So in our case, we are talking about primary pump circuit. So we have selected the primary pump circuit and segregated this circuit from the main project layout. And the details corresponding to this, the dimension or the length of the pipe for each section, A to B, B to C and so on, and the flow in each section. So this is all about the primary pump circuit, the length of the pipe in each section and the flow in each section. Okay, so what's the next step? The next step is to determine the critical path. So a little idea related to this I've already given you in the earlier lectures. So this is the critical path for us in case of primary pump circuit. Note that this is the path where the head loss is going to be the maximum. Alright, so what's the next step? The next step is to select the pipe size. For that, we'll use this chart. This has been already explained in detail in earlier chapters. Note that we are using the chart for closed piping system because we are talking about the primary circuit where water is flowing inside the pipe and this water is not exposed to the atmosphere in any part of the flow. It is completely inside the pipe. So we'll use the chart for closed piping system. Alright, before we move forward and try to find the pipe size, is something that we need to understand. Now, this is a snapshot taken from the ASHRAE handbook. This basically guides us and tells us the criteria to be followed while selecting pipe size. So, what's that? You can go on and read this thing. The entire summary is something that I'm interested in mentioning over here. So, if the pipe size is 2 inches, this is the nominal pipe size. So the pipe size is 2 inches or less. In that case, velocity is the criteria and its limit has to be 4 fps. This means for a pipe size of 2 inches or less, the maximum velocity of water flowing inside this pipe can be up to 4 fps, not more than that. It can be less than that, but not more than that. And let's say if there is a size, and let's say if there's a pipe of size more than 2 inches, in that case velocity limit is not the criteria. Instead, the criteria is pressure drop. So what is the maximum allowable pressure drop? 4 feet of water for 100 feet of piping. So if you get value anywhere more than 4 feet of water for 100 feet of piping, that value cannot be used. So please note, this is the criteria for pipe sizing. For pipe sizes 2 inches or less, velocity limit 4 fps. For pipe sizes more than 2 inches, pressure drop is the criteria and its limit is up to 4 feet of water for 100 feet of piping. Alright, now let's come back to this chart and see what are the parameters mentioned over here. The first one, friction loss, which is feet of water per 100 feet. So you get to see these values from 0.1, 0.15 and so on till 100. If I say the value is 25, this means 25 feet of water per 100 feet of piping. Okay, on the y-axis there is flow in GPM because all our calculations are in IP system. So we are using the GPM unit. Next we have the pipe size. So these lines are representing the pipe sizes starting from 3 by 8 of the inches till 24 inches. So these slanted lines represents different pipe sizes. Alright, is there any other parameter? Yes, there is. And what's that? That is velocity, which is mentioned in feet per second. That's FPS. So these are the lines of velocity starting from 1 fps till 30 fps. Please note, Carrier 1960 recommends that the velocity not exceed 15 fps in any case. So we cannot select any value beyond this. So maximum speed of water inside the piping can be up to 15 fps, not more than that. So this part of the chart will not be used in any case. All right. So we already know for primary circuit, the flow is 250 GPM and 125 GPM. So for 250 GPM, we'll see what value of pipe size do we get. So 250 will lie somewhere over here between 200 and 300. So this is the line corresponding to 250 GPM. So if you see, we don't get any line corresponding to the pipe size which intersects this line below 2 inches. You see, there is no 1.5 inch pipe size that intersects this line. So which line intersects this? This 2-inch pipe size line intersects this flow line like this. But can we select 2-inch pipe size? Let's see that. We already know the criteria up to 2 inches. That's 4 fps maximum velocity. We already know the velocity will exceed, it's more than 20 over here, so we cannot select this. Even if we try to follow the second criteria, you see the friction loss is going to be 100, which is obviously not a value that has to be selected. So we cannot select the 2-inch pipe size. Let's see, is 2.5-inch pipe size allowed in this case? So if we do that, this line intersects the capacity line over here. Now, if we draw a line from here to the friction loss line, it intersects at 40 feet of water per 100 feet of piping. Again, the maximum allowed value is 4 feet of water. Here we are getting 40. So we cannot select this 2.5-inch pipe size. So what's the other option available to us? That's 3 inches. So 3 inches corresponding to this, we get again value more than 4. So again, this is not possible. Next, we can go for 3.5 inches. Here also, we are getting more than 4. Again, not possible. Next, we'll select the 4-inch pipe size. So this intersects the capacity line over here. Mark this point. And when we draw a line from this intersection point to the friction loss line, we get a value slightly less than 4, which means this value can be taken. This is allowed based on this second criteria. And obviously, you might have already understood by now, since this is more than 2 inches, so this criteria has to be followed. So we are getting 4-inch pipe size, so we have to follow this criteria. So it's less than 4, so that's correct. But let's say we are trying to take a different value just after this one. So instead of 4 inches, if we select the 5-inch pipe size, in this case, we get the friction loss to be almost equal to 1. So we can also select this, but this is going to be highly over designed and cost ineffective solution. So we'll stick to the value that we already have, which is the 4-inch pipe size. So what is the pipe size we got from here? 4 inches. All right. So we have determined the flow rate, we have selected the circuit, we have determined the critical path, and we have also selected the pipe size for 250 GPM flow in primary circuit. What's the next step? To determine the friction loss. Corresponding to this value, we already have the value of friction loss, which is slightly lesser than 4. So we can say the friction loss that we're selecting is 3.8 feet for every 100 feet of water piping. Okay. The next step is to determine the velocity. Now, how to do that? When these two lines intersect over here, we have to draw a line parallel to the velocity line passing through this intersection point. So it's going to be like this. And this line lies between 6 and 8. That means between 6 fps and 8 fps. So what's the value? We can take 6.5 fps based on the location of this line. So these are the values that we have found for 250 GPM flow in primary circuit. Next, we'll determine the values for 125 GPM flow. As we already know, in the primary circuit, there are two types of flows in different sections of the pipe, 250 GPM and 125 GPM. So for 250 GPM, we have already determined all the values. Now it's time to determine the values for 125 GPM flow pipe section. So in this case, we'll just mark the 125 GPM between 100 and 150. We'll mark this value. And now we don't use hit and trial method. We already know the value of friction loss has to be less than 4. So based on that, we'll select this value, which is 3 inches of pipe size. So in this case, for 125 GPM, we are getting 3 inches of pipe size, and the friction loss is again almost equal to the earlier value that we found. So we'll again take 3.8. And if we see the velocity, it's anywhere between 5 and 6. So that value we can take as 5.5 FPS. So these are all the values that we need to find for each and every section of the pipe in primary pump circuit. So now moving on. Now we'll calculate the head loss, because we have already determined for 250 GPM the pipe size, friction loss, velocity, same for 125 GPM pipe size, friction loss, velocity, and these values we already had determined earlier. So these are the steps that we have already followed. The next step is to calculate the head loss. So now head loss calculation. This is the Excel sheet that we are going to be using to calculate the head loss for primary circuit. Here you can see in the first column we have the section, then flow, then pipe size in inches, then description, which is basically the components in that network, then the friction loss, length of the pipe or fittings, then number of fittings, then equivalent length of fitting. Now this is important to understand. See, what actually happens for a pipe, we can put the value of length, but we cannot have the length of the fitting. That just doesn't make any sense. So the way the tables and charts have been prepared, what it does, you can convert the loss of the fitting in equivalent length of the pipe. Let's say a fitting causes 5 feet of water column. So what length of the pipe has to be there which will give the exact same head loss? So that value of pipe length is known as equivalent length. So we basically convert the losses caused by the fittings or valves in the equivalent length of the pipe. So after doing that conversion, we'll just put those values over here. And then finally, we'll get the total equivalent length, which is basically the addition of the length of the pipe and the equivalent length. So when you add these two columns, you get this column. And finally, head loss in feet of water. So these two columns are actually calculated directly by this Excel sheet. And you have this Excel sheet in your course. Make sure to download it and use it later on. Okay, moving on. First, we'll bring the entire project. We already have found these values earlier. So first, we'll see what are the different sections we have in this circuit. So first of all, you see there's a section from here A to C. Now, why are we selecting this? Because for this section, the flow is same. The flow is not changing from A to C. So we'll just call it one section from A to C. So this is A to C. Now what is the flow in A to C? We already know it's 125 GPM. So we'll just mention it over here. And what is the pipe size? For the section A to C, which has 125 GPM flow, we have already determined the pipe size, which is 3 inches. So we'll note it down over here. All right. What is the next section? The next section is C to E. Why? Because just keep in mind that whatever sections we are talking about are the sections of the critical path. We are not interested in any section which is not included in the critical path. So all these sections that we are going to be talking about is a part of the critical path. So A to C we have already taken. The next section is going to be C to E. Why? Because it has the same flow. After E, the flow changes. So from C to E, there is same flow. So we'll just write C to E. And what is the flow? What is the flow in C to E? We know it's 250 GPM. So we'll just mention 250 over here. And what is the pipe size? So for 250 GPM, pipe size is 4 inches. So we'll mention over here. Next, what is the next section after E? So E, F, G, H. From here to here, we know the flow is 125 GPM. So we'll just call it another section. So E to H is one section. What is the flow? 125. And what is the pipe size? For 125, it's 3 inches. So we'll just note it over here. And finally, we have from H to K. So H2K is the last section. The flow 250, and for 250 we already know the pipe size is 4. You can see from here also for 250 pipe size is 4 inches. Alright, so we have found all these sections and their corresponding flow and pipe sizes. What are the components in these sections? So from A to C, what do we see first? From A to C, first of all, we have the pipe. Alright, so we'll mention pipe over here. What do we have next? So as we move from A to C, we get the three-way plug valve, we get the balancing valve, we get the gate valve, we get the T, and we get the reducer. So we'll mention all these over here. The three-way plug valve, balancing valve, gate valve, T, and the reducer. Okay, in section C to E, what do we have? In section C to E, we have pipe, obviously. Then we have the T, which is over here at exactly C. Then we have the elbow, 90-degree elbow at D. And then we have another T over here at E. So we'll mention all these components over here. We have the pipe, we have the T, the elbow, and then one more T. Okay, in the section E to H, in the section E to H, this section, what do we have? First of all, we have the pipe, all right. Next, we have the elbow over here, 90-degree elbow. Then we have the butterfly valve. Then we have the strainer. Then we have the check valve. Then balancing valve. Then we have the butterfly valve. But these two will be written together. So that's all we have. And again, we have the 90-degree elbow, but that is something we have already taken earlier. And then we have this T. Okay, so we'll just mention all these components over here. We have the pipe, then we have the elbow 90-degree, this one, then we have the butterfly valve, this one, then strainer, check valve, balancing valve, strainer, check valve, balancing valve, and then this final T over here. Okay, now let's talk about the section H2K. So in H2K from here to here, what do we have? We have the pipe. Okay, we have the elbow over here and here, and then we have the butterfly valves. So the pipe, the elbow, and the butterfly valve. So these are the components in respective sections of the pipe. Okay, so what are the friction losses now? So in A to C, which has 125 GPM flow and pipe size is 3, what is the friction loss? Over here, 125 GPM we earlier determined was 3.8. So in this section, 3.8, and in 250 GPM flow, 250 GPM flow, it's 3.8 again. So again 3.8, again 3.8. Because 125 flow is having this much of friction loss, 250 this much. So again 125 flow, so again same value, and 250 again repeated, so again same value. So everywhere we have the same friction loss. Now it's time to calculate the lengths. You see in this section A to C, what is the length? From A to C, what is the length? See, A to B and B to C, so 8 plus 15, that's 23. And what are we gonna write in number of fittings? So here we are only talking about pipe, so in fitting we'll just mention 0. Okay, so three-way plug valve, obviously it will not have any length. This balancing valve, they don't have any length. Length is only for pipes. So either you'll be putting values in this column or this column, not both of them simultaneously. It has the value, so here it's going to be 0. So here it's 0, so here there will be some value. So it's like that. Okay, so for three-way plug valve, the length is 0. And how many valves do we have? From A to C, how many three-way plug valves we have? We have only one over here. So we'll mention one over here. Then we have the balancing valve. So for length of the balancing valve is going to be 0. And how many fittings? How many balancing valve we have? We have only one balancing valve. Again, this is 0. How many gate valves? Over here, only one gate valve. Now don't get confused. This is also another gate valve. This is not included in the critical path. Critical path is like this. So in this critical path, there's only one gate valve. So we'll mention that over here. Again, this is 0. How many T's? One T over here. So we'll mention that. Reducer. So you see there is one reducer because there is different flow in this and this section. Here flow is 125, here it's 250. So we need a reducer over here. So that reducer we have and its length is 0. How many reducers we are using? Only one. All right. So in the same way, we'll see for section C2E. So C2E is from here. C2E. We have the pipe. What is the length? C2E. C2E. See, C2D is 15. D2E is 5. So total length is 20. And number of fittings obviously 0. And the length of the T 0. And how many T we have? Only one. See, we do have a T at C, but that's only one. Okay. Next, elbows. How many we have? Only one elbow over here. Then we have another T, which is the branch flow T. Length 0. How many? Just one over here at E. This is the branch flow flowing like this. Okay. Then in section E to H. In section E to H, which is from here, E to H. What is the length of the pipe? See, E to F is 5, F to G 10, G to H 5. So the total length for this is 20. And number of fittings 0. Elbow, now its length is 0. So how many elbows do we have in E to H? In E to H we have this 90-degree elbow and this 90-degree elbow. So two elbows we have. Butterfly valves, we have one over here, another over here. So two valves we have. Strainer, just one over here. Check valve, we have only one check valve over here. Balancing valve, only one over here. Okay, then T branch flow, obviously its length is 0. How many T's do we have? We have only one T over here, which is the branch flow. Flow is like this. So 1 T. Alright, now in the last section, H2K. H2K. First of all, the length of the pipe, H2I5, I2J8, J2K 5. So total length is 18. This is 0. Again, the elbow length 0. And number of elbows, how many do we have? One over here, another over here. So two elbows we have. And butterfly valves, 1, 2. So the length is 0. And how many valves do we have? Two butterfly valves. So this is how we'll note down each and every value from the project and some other data that we already found earlier. Okay, so now we'll fill the column of equivalent length of fitting. So to do so, first of all, in the first column, we see that the pipe. Now the pipe has a length of its own. So that's the reason why over here we are only putting the equivalent length of the fitting. So for pipe, it's going to be 0. Alright, now for the valves and other connections, there are tables that have already been shown to you in the earlier lectures. So we'll make use of those tables and charts and fill the values in this column. So first of all, let's see this chart. So here we have the three-way plug valve. Now over here we don't see anywhere the three-way plug valve values. So we'll just leave it as of now and check for other valves. So here we have the balancing valve. So do we have the balancing valve over here? Yeah, we do have over here. So we'll select this row. Why? Because here we have the pipe size as 3 inches. And over here this balancing valve is attached with a pipe of 3-inch diameter. So for balancing valve attached in 3-inch pipe, there are two options possible, 60-degree Y and 45-degree Y. So we are just taking 45 degrees Y and we get the value as 35. So we'll fill this value in this Excel sheet. So here we have 35 and here we have the 35Y because again here we have 3-inch pipe size with a balancing valve. So here also we'll put the value at the same time. Okay, next is gate valve on a 3-inch pipe size. So here we have the gate valve. So gate valve on a 3-inch pipe size, the value is 3.2. So here we'll fill the value as 3.2. Okay, next T with a branch flow. Here we don't have any value of T. Reducer is also not here. So we'll just leave these two values. Again pipe. We know the value is going to be 0. Okay. Then we don't have T, elbow or any other T over here in this chart. Next, again pipe, again 0. Elbow, we don't have. Butterfly valve, we don't have. Strainer. So do we have strainer? Yeah, we do have a strainer over here. So let's say the strainer that we're talking about is a flanged end. If it is screwed end, we'll take this value. But as of now, I'm just assuming the strainer is flanged end. So its value is 42. So this value will mention over here. Okay, next, check valve. So we also have a check valve over here, lift check and swing check. So we have the valve that we have is swing check valve. So for swing check valve and 3-inch pipe size, the value comes out to be 30. So we'll mention 30 over here. Okay. The next we have balancing valve that we have already substituted the value for. Then the T, we don't have T in this table. Again pipe, again 0. Elbow, butterfly valve. This is what we don't have in this table. So these are some of the values that we can use from this table and put it in the Excel sheet. For remaining values, we'll refer to the other table. So let's check that out. This is the other table. Okay. Now we are looking for, first of all, three-way plug valve. So we do have three-way plug valve in 3-inch pipe size, which is over here. And the value that we get is 7.67. Here we have the through and branch, so mostly the flow is through. And in our case also, if you see the project, the flow is a through flow, which is a straight flow. So what value do we get? 7.67. So we'll put this value over here. Next we have T reducer. Again, we don't have these values in this table. T, we don't have elbow, T's, elbows, butterfly valve. So do we have butterfly valve? Yeah, we do have over here. So for which size pipe? For 3-inch. So for 3-inch butterfly valve, the value is 11.51. So 11.51 will note over here. Then the next is T for branch flow. We don't have in this table. Elbow we don't have, butterfly valve we do have for 4 inches. So for 4 inches butterfly valve, the value is 15.10. So we'll note this value over here. So by taking the values from the two tables, we are having these many values, but few of the values are still remaining. So we'll use another table for this. So this is another table. From here you see we have the pipe size, then the T's over here and the elbows and bends over here. So first of all we'll see the T for branch flow for a 3-inch pipe size. So for 3-inch pipe size, flow through branch. Okay, here also you see T is the flow in this T is branch flow. Here also branch flow. So what value do we get? 15. So we'll mention 15 over here. Here also you see T for branch flow for 3-inch pipe. So here also we'll put the value at the same time. Reducer. We don't have reducer over here. Okay. Any other T? Yeah, we do have T for through flow for 4-inch pipe size. So for 4-inch pipe size, the T straight through flow. Through flow and straight through flow means the same, means the flow is straight. If it is not a branch flow, it's a straight flow. So in this case, what value are we actually getting? We are getting 6.7 for a 4-inch pipe size and straight through flow T. So we'll just put this value over here, 6.7. Next we have the elbow of 90 degrees for 4-inch pipe size. So for 4-inch pipe size, elbow 90 degree, what value do we get? 10. So 10 over here. Again, we have T for branch flow, 4-inch pipe size. So for 4-inch pipe size, T for branch flow, what value do we get? 21. So 21 over here. Next, we have elbow 90 degrees for a 3-inch pipe size. So 3-inch pipe size, 90 degree standard elbow, 7.5 is the value. So 7.5 over here. So you see we almost have all the values. We just need to find this value of reducer equivalent length of fitting. Okay, so we'll find that. Before we go into this, first understand how does our reducer looks like in the project that we have. First of all, if you remember from here the flow was 125 GPM and here it was 250 GPM. And the pipe size that we found was 3 inches over here and 4 inches over here. So this is a reducer between a 3-inch pipe size and a 4-inch pipe size. Okay, keeping this in mind, come to this table. We are looking for a 3-inch pipe size, so select this row. Then what do we have? Do we have sudden enlargement or sudden contraction? To understand this, just follow the direction of the flow. We know the flow is from top to bottom in this direction. So the flow is experiencing sudden expansion or sudden enlargement. And that's the reason why we have a reducer over here. So we'll select sudden enlargement column. And if you see, we have three options over here: 1/4, 1/2 and 3/4. So what's this? If you see carefully over here, this is small d upon capital D. Small d is the diameter of the smaller pipe and capital D is the diameter of larger pipe. In our case, the smaller pipe has a size of 3 inches and the larger pipe has a size of 4 inches. So if we do the ratio small d over capital D, we get 3/4. So 3/4 is this column. There can be other cases where, let's say, this is 2 inches, this is 4 inches. So if we do the ratio, we'll get 1/2. In that case, we'll select this column. And if we have any other case where value is, let's say, here we have 1 inches, here we have 4 inches. So the ratio is going to be 1:4. In that case, we'll select this column. But in our case, the values that we have, the ratio comes out to be 3:4. So we'll select this column. And for 3-inch pipe size, the final value that we're getting is 2.6. So we'll take this value from here and mention this value in the Excel sheet. So now we are done with the column of equivalent length of the fitting. We have used all the tables and found all the values that are relevant for this column. Now, after all the values are substituted, the Excel sheet will automatically give the total equivalent length in feet. So once you feed all these values, this column will be automatically calculated. And so on, this column will also be automatically calculated. So once the summation of all these are done, the final value will also be calculated automatically by the Excel sheet, which comes out to be 14.91 in this case. So the head loss due to friction we found for the primary pump circuit is 14.91 feet of water column. Okay, so now we have calculated the friction losses from A to B to C to D, E, F, G, H, I, J, K. So from A to K, we have calculated the head losses due to pipe and all the accessories attached to it. But there are also going to be losses due to the evaporator coil inside the chiller. So when water flows through this coil, obviously this evaporator coil will also contribute in some amount of head losses. So we'll have to consider that also and add to the total loss that we have already calculated. So we'll find that. So this is what we already have calculated using Excel sheet. We'll again make use of this sheet that we have already studied earlier. If you remember, we selected this row and this. If you remember, we selected this row 104.5 tons and we selected flow from here and here. But this time we are going to select this column where the evaporator pressure drop is mentioned in feet of water. So corresponding to this tonnage and this value of evaporator flow, what is the evaporator pressure drop? This is 15.4 feet of water. So we'll add this value to the value that we already calculated. So when we add these two, the total comes out to be 30.31 feet of water column. Now we'll add a safety factor, let's say around 15% to this value. So once we do that, we end up getting the final value as 34.85 inches of water column. All right, great. Now let's move forward and see what we have to calculate next. This is a really important value in the entire calculation that we have done. This is the total head loss due to the pipe, its accessories, and the evaporator coil. So the pump has to overcome this much of friction losses. It is only then possible to circulate water in the primary circuit. So we have followed all these steps Let's see what is the next step. So the final step is to select the pump. So now we'll do pump selection. For that, we'll use this basic formula. Here, this is bhp, which is the horsepower. This is specific gravity. It is nothing but the density in CGS unit. For water, we know specific gravity is 1. This is GPM. Now, this is very important. This GPM is actually the flow through the pump. So, whatever is the exact amount of flow through the pump, that value we have to substitute over here. This H is the total head loss that the pump has to overcome. This 3960 is a constant, and this is the efficiency of pump. When we put the values, specific gravity of water as 1, the GPM as 125. Now over here, some of you might be confused that why are we choosing 125 GPM? Why not 250? Now the reason is very simple and clear. The flow across the pump is 125 GPM and not 250. 250 GPM is the flow across the main pipe. But if you exactly see the pipes near the primary pump, the flow is 125 GPM. So we have to use that value. Then the head loss the pump has to overcome. This is 34.85 that we calculated from here, 3960, and the efficiency I'm taking as 85%. On calculating this value, we get 1.29 HP. So what is the power of pump that is required in order to overcome this much of friction? 1.29 HP. In SI unit, this is approximately equal to 1 kilowatt. So the pump that has to be selected in order to facilitate this process is 1.29 HP or 1 kilowatt. Now, if you remember, we have chosen two primary pumps. So each of the pump has to have 1.29 HP. Then only the flow and the cooling can be maintained. This is one quick way to select pump or to calculate its brake horsepower. Now this is not necessarily the best way. Why? The reason is you might not get the pump having exact HP that is calculated from here. From here we are getting 1.29, but in the market, let's say it is not available. So what to do? We can go for the next model available. Also, there are few other values such as impeller diameter, the NPSH requirement. All those values and their ideas we are unable to get if we do pump selection by this quick method. So we'll select the more detailed, a better method to select pump. So now we'll understand how to do pump selection in a comprehensive and the best possible way. First of all, we'll mention the capacity or the flow rate across the pump, which is 125 GPM in our case, and we have approximated the head value to be 35 feet. So the first step is to determine the pump model which is suitable for given capacity and head. This is one of the manufacturer of pumps, Fristrum pumps. So we have taken the catalog of Fristrum pumps. On the horizontal axis, you see the flow rate in IP as well as SI unit, and on the Y axis, you see the head in IP as well as in SI units. And these different curves are actually the family of curves or curves for different models. So based on the flow and the head, different models can be selected. The capacity that the pump has to overcome in our case is 125 and the head is 35. So we'll plot these two values in this graph. So 125 is going to be somewhere over here between 100 and 150, and 35 is going to be somewhere over here. So we'll draw lines from there. These two intersect over here. Now you see this intersection point is just beyond this 3521 curve. So in this case, we cannot select the model 3521 because it is not intersecting on or below this curve. So what to do in this case? What is the model that is available just after this intersection point? So we get this curve. So this curve means the model that we have to select is 3531. So the first step is done. We have selected the model as 3531. So out of all these models, the model which is suitable to overcome 35 feet of head and maintain a flow of 125 GPM is the model 3531. Okay, let's see what step 2. Step 2. Determine the impeller diameter and the power requirement. So here we have the characteristic curve of the model 3531. There can be various options in the same model 3531 based upon different impeller diameter, different power requirements. So we'll see within this 3531 model what power and what impeller diameter pump we have to select. So again we'll plot 125 and 35 on this graph, and these two intersect at this point. We'll draw this line from here. This gives us the impeller diameter, which is 155 mm. Please note, if this intersection point lies beyond this curve, then we have to select the very next curve. So if let's say this is the intersection point, in this case we will select this curve. And in that case, the impeller diameter is going to be 160 mm. But in our case, the intersection point lies on this curve. So we'll select this curve. And we get the value of impeller diameter to be 155 mm. So we'll just note it down over here. 155 mm in inches, it's going to be approximately equal to 6 inches. Alright, next is the power requirement. You see, these are the lines of power. The intersection point lies between which two power lines? These two power lines that you see in red. And any pump selected within these two lines, all of them will have a power requirement of 2 HP. From the calculation we can get any value, but it is not necessary that exact power pump is available by any manufacturer. So they do manufacture pumps in different ranges of power. So for this model, 1 HP, 1.5, 2 and 3 HP. These are the options possible for power consumption. Based on the capacity and the head, the value that we are getting lies anywhere between these two lines. So the pump that we have to use within 3531 model will be consuming 2 HP of power. So the power that is required to run this pump is going to be 2 HP. Okay. To check NPSH. The concept of NPSH is very complex and it has been explained in great detail in the chapter of pumps in the earlier chapters. So make sure you refer to that section to understand about NPSH in great detail. Over here, just simply understand NPSH stands for net positive suction head. So there has to be some amount of head available, and that is something that we have to check within the graph. This helps in avoiding cavitation. So how do we check NPSH value? We need to draw a line from this intersection point till the NPSH curve. So it intersects the NPSH curve at this point. From this point, draw a line that intersects this axis. Here NPSH values are given in feet. So the value that we get is 6. So the NPSH required is 6 feet of water column. So the installation must provide at least 6 feet of head. This means if you are using this pump, model number 3531, impeller diameter 6 inches, power 2 HP. In this case, the NPSH requirement is 6 feet. So in the actual location of the project, there has to be at least 6 feet of head available. If the net head available is less than 6 feet, and in that case, if we use this pump, then cavitation will take place. So this is something really important to take care of, that the NPSH required is given by manufacturer, that we can understand from the curves. So in the actual project location, the NPSH available has to be more than 6 feet of water column. Alright, so this is how we do pump selection in detail. Now we'll quickly go through the steps involved in the primary pump selection. The first was to determine the flow rate. If you remember, we have used the AHRI standards and determined the flow rate in each and every section of the pipe. Next is to select the circuit. So we have segregated the primary pump circuit from the main circuit and only focused on this circuit and calculated everything accordingly. The next step is to determine the critical path. You remember we have determined critical path like this. Then we selected the pipe size using the charts and tables. After that, we have determined friction loss and then we determined the velocity from the same chart. And these are the values that we obtained for pipe size, friction loss and velocity for different flow in different sections of the pipe. Next step is to calculate the head loss. We have used the Excel sheet and calculated the head loss. Alright, and finally we have selected the pump. So using the detailed method of pump selection using manufacturer's catalog, we have selected the Fristrum pump model 3531 with an impeller diameter of 155 mm, which is approximately 6 inches, and the power required by this pump is 2 HP, and the NPSH required on site for this pump to function is at least 6 feet of water column. So this is the overall steps in sequence that we have to follow in order to size the pipe and select the pump. Now this same method and same sequence will be followed for pipe sizing and pump selection of secondary pump circuit or condenser pump circuit. Alright, so this was all about the primary pump head calculation and selection. Hope you enjoyed the session. See you again soon in the next one.